As was said, my name is Tomas Drab. I work as a hardware security engineer here in Abu Dhabi in Zenith Labs. My colleagues asked me to give a talk because you know all this cool stuff, how to take apart the chips so you can create something. So here I am. I would like to tell you a little about failure analysis and how can we use failure analysis tools for reverse engineering. So first, I will start a little about my background. I will tell you all the boring list of failure analysis tools we can use. Then some interesting part, how could we make it cheaper? And I will show you some use case, which is still kind of work in progress. So I studied microelectronics in Brno University of Technology, which is in the Czech Republic. Then I started to work as a failure analysis engineer for 6 years. I was responsible for the whole analysis from failure verification to failure localization and all these cross sections and all the physical analysis up to the end to the finding of the root cause. And since last year, I work in Zenith Labs here in Abu Dhabi. So, how many heard of failure analysis? Basically, all the major chip manufacturer has these huge labs which are heavily over-financed, and there's a good reason behind it, because in an early stage of production or in a development phase, you need to find every root cause of the failure so you can eradicate it in the future. And they invest a lot of money to all kinds of fancy tools. In failure analysis, we are using variety of physical phenomena to highlight traces, to localize failure, to localize some leakages, determine material composition, and also all kinds of mechanical tools which can help us prepare the sample for imaging and basically take it apart. So what would you do if you have a chip you know nothing about? Yeah, X-ray is an answer. You can see through the material with using high energy beam or high energy wavelength electromagnetic radiation. Sorry. We know 3 types of X-rays. X-ray tube, which is most common. Maybe your dentist has one. Transmission target. This is for creating really high resolution images. And if you want to go like super high resolution, you need to go somewhere to Switzerland to the synchrotron facility. Good thing about X-rays, it can tell us something about wire bonding, location of the chip, if there are more than one chips, and also if you have a BGA with some PCB under the chip, you can reverse engineer the PCB using 3D X-ray tomography. Basically, you rotate the chip and image it from all the angles, and you can recreate the whole structure. Okay, once you know what's inside, we can somehow open the chip. We can go chemically or physically, using really strong chemicals like fuming nitric acid and sulfuric acid. You can etch the mold compound away, and all you have left is the bare die with if you're lucky, with the wire connects. If you're not lucky, the wires are copper, and there's a whole lot of other trouble. And you can use this fancy machine which can automatically change the ratio of chemicals, adjust temperature, and it's basically touch and go machine. Or you can go physically. You can use laser to basically burn away the mold compound, and you will still have some residue of mold compound, and it's good to remove it using plasma etching. You use basically oxygen plasma to burn away the residual plastic. Okay, now we have open chip, and we want to look at the die. So optical inspection, like every lab has to have optical microscope. We can do visible light inspection. I would say you are all familiar with it. And we can go infrared. Nice thing about infrared is that we can see through the silicon, because silicon is transparent for the infrared light around 1000 nanometers. And we can take a look through it. And also we can use ultraviolet light, mostly for high resolution imaging, and using, for example, focal microscope with UV laser scanning the surface. We can create 3D reconstruction of the surface, for example. Okay. Now we know about the surface of the chip, and we want to go deeper. We can etch away the layers, either use wet chemicals or dry chemicals. Wet chemicals are usually the most dangerous chemicals on the planet. You don't really want to mess with it too much. And also you can use dry chemicals. It's again like plasma decapsulation. Here we use just other gases to etch metals, silicon oxide, silicon nitride, and all this layer after layer. Or we can use some mechanical polishing. We are using really fine grain materials like diamond lapping films or aluminum oxide powder, which with the grain size, I don't know, like less than 0.01 micrometer. And with that, we can remove mechanically layer after layer. It sounds easy, but there's a lot of skills involved, and the machines like this can help us, but still it requires a lot of adjustment and a lot of maybe years of doing it to make it perfect. But then you can basically go down layer after layer up to the polysilicon or transistor layer. Okay, once we uncovered top layers and we gain access to, I don't know, memory, we would like to probe it. Yeah, so probing is basically putting contact directly to the chip lines, and we can measure some signals there. We can do microprobing. It's better for, we're using like optical microscope with the probes. Usually the tiniest are 0.25 micrometer tip. And it's better for some upper layers. If you want to go to probe the lower layers, you need to go nanoprobing. Here you have to have a scanning electron microscope. You just cannot do it in optical microscope. And by using these piezo movement probes, you can very precisely land the probes on a structure with like sub-nanometer precision. Okay, as I said, silicon is transparent for infrared light, and when we want to gain access to the backside. Backside milling is a super useful option. You can basically preserve all the chip functionality while creating an opening on the backside and gaining access to the chip, and you can see the structures. You can and the bare die is vulnerable for example, laser fault injections. Yeah. And what if I tell you that you can see the current flowing through the chip? Like standard LEDs, which produce light, every semiconductor component also produces light. Only drawback is that it's very weak and it's in infrared. But if you have proper tools like super fancy camera with flipped cooled chip, usually you can not only have like silicon-based chip, but indium gallium arsenic, for example, which can detect infrared light much better. You can see the current flowing through the diodes, transistors. And for example, if you have SRAM memory, which is basically two inverters running in a circle, you can use it to basically see what is stored in the memory. Okay, just a quick localization methods. If you have some short in a circuit, it produces heat, and by using liquid crystals, the liquid crystals have this really strange forgot the word. So they can change its optical properties at the certain temperature. So once you reach the temperature, it changes the crystallographic orientation, and suddenly the light isn't going through, and you can see this dark spot where probably the failure is. Similar method, but more expensive one, is thermal emission microscopy. Basically, you're using very expensive thermal camera with specialized beryllium optics to see the same thing as with liquid crystals. Okay, Obierge, Liva, Tiva. These are all, Obierge means optical beam induced resistance change. Basically, if you scan the circuit with the thermal laser, which is usually about 1300 nanometers, you can introduce some heat into the circuit, and once you hit the failure or some short, it changes the resistance, and you can measure the change of the current and then localize precisely the failure. Usually it's part of the much bigger system, very sophisticated, using all kinds of sensors. You can go front side, back side. It has several cameras, and you can get to the price tag of $1 million. Okay. Scanning electron microscopy is essential if you want to analyze today's chips. You can get down to 1 nanometer precision. You basically hitting the surface with the electrons, and you can detect all kinds of scattered or reflected electrons, and it can provide whole variety of information which we can use. For example, it creates a characteristic X-ray and we can determine the material composition. This is very useful when you want to chemically delayer some chip and you don't know nothing about layer. Do first the analysis and then proceed with delayering. If you want to do some adjustment in the chip, focus ion beam is the tool you have to go to. It's basically like the SEM, like the scanning electron microscope. Just instead of electrons, you're shooting ions, which are much heavier, and you can remove the material using this really fastly accelerated ions. But not only that, you can also deposit material. So imagine if you want to create some connection into the deeper structure. First you create a hole in a chip to gain access to the trace. Then you can fill it with tungsten, for example, and create the landing probe landing site where you can then microprobe the chip and sniff some data. Okay, here are some other techniques which are used. Electron beam induced current. You're using electron beam to create an electron hole pair, which are separated in the depletion region, and then the current can be measured and you can recreate the structure of the transistor, for example. And using a similar technique, you can trace wires in a chip. So when electron hits the trace, it travels to the probe, and probe measures the current, and according to that you can see basically the whole net. Okay, here are just a list of evolving methods, and I think you will have somewhere possibility to download the slides so you can review it. And okay, how to make it cheaper? So basically you can replace all the expensive equipment with your skills. Like my colleagues noticed that he's doing it wrong. Or you can buy just commercial electronics and change it to your purpose. Or there's a whole second-hand market of used tools because technologies are getting better, and the manufacturer are getting rid of the old tools. Or there are plenty of laboratories where you can hire them to make your chip adjustments, for example. Okay, I talk about infrared microscopy. So unfortunately, you will have to have the microscope. Yeah, you cannot avoid it. What you also would like to have is infrared lens. If you find some lens on the eBay, go for the red one. Usually it means infrared. It has low attenuation of infrared light in optics. And then you need to somehow to create an infrared light. Yeah. Usually in modern systems, they're using lasers, but these are expensive. What is much cheaper are infrared LEDs. So just create a LED ring and illuminate your sample. Or if you have wide spectrum white light, you can use some filtering. In my past, I just used a piece of silicon to filter white light and create an infrared light, and it was working just fine. So just use some old chip. And Also, you need to somehow detect the light, yes, because you cannot see it with your eyes. If you want to just view the chip from the backside, I think it's easy. You can just buy any camera and remove infrared filter, and probably you're good to go. If you really want to see the current and do a photo emission analysis, then you have to invest a little more. You would like to go to some cooled camera. Usually there are dedicated cameras for astrophotography, and inverted chip is also kind of nice because it collects much more light. Okay, decapsulation. Here we can remove all this expensive equipment and use just the skills and some small chemical tools like pipettes. Basically, you just use the chemicals to drop small drops of chemicals on the chip and slowly etch it and until you reach the chemical. So this is quite easy. I'm sure at the beginning you will destroy some chips, but eventually you will learn it. And remember, safety first. Okay, IC delayering. I showed you really like expensive fancy machine how to which can delayer the chip, but you can actually do it using just your finger. Yeah, this is like old method before they introduced all these fancy machines. You just need proper grinding material and just put the chip on your finger and grinding, and it just takes a lot of time, a lot of patience. You also will destroy some of the chips, but eventually you will learn the skill, and then you will be able to delayer basically any chip. All you need is some hairy cloth like velvet, which can hold some medium. You need some grinding material, like really fine grain powder, like aluminum oxide or silicon oxide, and some high viscosity medium, like glycerin, and I think also like olive oil would work. Okay, lasers are outdated, so at least for the IC editing. That's why you can easily find it used somewhere on a second-hand market, because all these manufacturers are using FIPS now. But still, if you want to gain access just to the second layer and you just need to remove the passivation, this really nice tool to have. Doesn't cost fortune, and also it's not that precise as FIP, but it can be really useful for like really small price comparing to FIP. Okay, and at the end, I would like to show you some example of reverse engineering. It's still not finished work, but okay. We have a 8-bit microcontroller which has a programmable fuse which locks the flash memory, prevents from firmware dumping or software dumping, and these fuses are located under the flash and are covered with the shield. So, this shield prevents it from deleting with using UV light, for example. So let's go take a deeper look inside. So what we can do, we can delayer the chip and analyze layer after layer. So as I showed you, we use the machine to delayer the chip and remove first layer. This is second metal, and this is third metal, or like as manufacturer says, this is the first metal. But okay, and here you can see the the fuse. Basically, it's a memory cell. It's a flash memory cell. Maybe it's a little bigger, but essentially, there's nothing special to it. We only didn't understand like what's this extra connection to the gate, but you will see later. Okay, we did a cross-section analysis. I don't know if you can see it properly, but basically here is the actual memory cell. We did it for analyzing the extra contact to the gate. So how to do reverse engineering? Basically, you can easily see the transistors. Yeah. So, for example, here you have one transistor. Here you have second. Yeah, and like that you can redraw the circuit and end up with something like that. I called the programming lines program and program 2, and this is the output of the fuse or the memory cell. Basically, this part and this part serves for writing or erasing the value, but actually we don't care about it. I will show you why. Because when we trace it back to the top, we can see that there are lines which are directly connected to the memory cell, and we can actually see the lines from the surface of the chip. Now, I think the easiest thing would be to just hire some external laboratory. Hey, can you make an opening here, and you can write anything, erase anything. You can change the output of it. Yeah. What's the tricky part? There are like 9 of these memory cells, and they might be in some combination, but probably that's a next year talk. Okay, just to quick recap, failure analysis is a whole industry, and which uses really fancy tools which we can use for reverse engineering. Not every tool has to be in millions of dollars. We can replace it with some skills and some little knowledge. These tools are becoming cheaper. Commercial electronics are getting better. So this is also our advantage. And complete reverse engineering is not necessary if you have access to the correct lines. Thank you for your attention.
Thank you, Tomas. Are there any questions from the audience? No? Then we'll head to the Slido. Shall I read them for you? Or will you read them yourselves?
Okay. The power of laser to inject. Well, it depends on the material on the surface. It's not easy, but you have to try. It's ideal if you have like more samples to play with. The next one? Okay. What is the best way to convert the hardware value? Oh, I'm not sure about this.
Just take the next question.
Yeah. Quite familiar with the article, but what was it the hardware implant or the change of the?
Could the person that asked the question, could he elaborate? Is he in the audience? Could the person who asked the question elaborate on the question?
So I didn't ask the question, but in the Bloomberg article from a year ago, it was alleged that a printed circuit manufacturer added a chip on a bus from a server and replaced I think it was a signal conditioning chip with a more sophisticated microcontroller that would then allow
probably it was not
memory corruption.
Probably it was not circuit edit like I explained. It was the whole change of the chip by the manufacturer. So no.
All right. Any more questions from the audience? Then I'd like to thank Tomas Drab, and please give him one more big applause.
Thank you.